So, good evening, guys. I hope you all are okay. You all are enjoying your life. So happy to see you all again. With this, let me first welcome all of you on behalf of Sunbeam. And we are starting with, the building your own LM from scratch. When I thought of this series, first thing that came to my mind, like, why would people want to come for this kind of course and they want to learn LM from scratch? Let me tell you the story behind it so you can understand like why I thought of it. So what happened here is like as I mentioned, I'm a freelancer, so generally I work with many clients. And for getting the project, I need to also pass a couple of interviews as well. When I'm working with the clients, overseas clients, of course. So in the month of, I think, January end or February 2025, I'm talking about. So I gave an interview to one of the companies. I won't disclose the name here. And I was hoping to get a project from them. And one of the CTOs, he was a kind of, a very well-known AI engineer there. And he was having quite a good experience in AI. I mean, literally writing the AI code. And he took my interview. So after, I think, a week or so, I got the feedback. Yeah, this person has got a good knowledge, but it seems like this person lacks how the internal things has to be done. I mean, he asked a couple of questions like, what do you mean by KB cache, or how will you improve, let's say, LLM performance? What are the hitch or hacks that you can go for? How will you implement your own quantization model? How will you use LoRa to go for fine tuning the project, fine tuning your LLM, and many different questions out there. I answered most of them, but couple of them which are very, very, very minute details, I couldn't answer them. And that's what he got. And I got a feedback from the other person whom I was talking with. He said, it's good, like everything went well, but this person wants you to work on the calling API basis, not to the one that they're working on. Then I got a little bit frustrated. I said, like, what the hell? I mean, I thought maybe I can work on that, but I was getting something else, which I was not willing to work on. It's like using the LangChain and calling the APIs. I was not willing to do that. I was willing to go inside it. Then I found like, okay, that's something I need to learn on. So in the month of February, I think first week or second week of February, I started digging around it. Like, how do I do it on my own? So I could get the entire LLM learn or entire LLM created from scratch. And then I came to know there are multiple resources available which can be used in order to understand what exactly goes beneath. So generally, people do not take interest in such things, but there are many opportunities out there in the world where if you know what happens beneath, you can solve many different problems there. One of the problems is something like when there is a problem, when the maybe the API is not working properly, or let's say LLM is not giving you the correct answer. It's kind of hallucinating. People generally go for something called the prompt engineering, and they try to solve the problem by changing the prompts. Sometimes it works, most of the times it does not. So there you need this kind of knowledge, and then you can solve any problems that you are kind of facing with. So probably you can find solutions immediately if you know how the things that you're working, it's kind of made from scratch. That's the reason what motivated me not only get this knowledge and keep it with myself. It's better I can share it with you all, so you can all also get benefited. And in the introductory video, I also mentioned like, maybe the frameworks will change. Today you are using LangChain, tomorrow you might use something else. Today you are using PyTorch, TensorFlow, tomorrow you might use something else. The fundamentals will not change. The math behind it will not change. What changes? Language. What changes? Framework. What changes? Mindset. You will never see the fundamentals are going away. And that's the reason why we thought of creating this course and sharing this knowledge with all the others. That's a motivation behind it, just to give an idea about it. So why did we start with this? So let me talk about this problem in details, like what exactly the problem we are facing today. I mean, when I say I'm using AI, what exactly people are doing, what exactly people are saying that they are into AI and they are doing something called an AI engineering. First of all, many of the AI developers or ML developers today, they are using LLM as a kind of a black box. So basically, you are a developer. This is your program. Say, for example, this is my program. And what you do in the program is like you call the APIs. So this could be a kind of direct APIs. Like, for example, you want to go for OpenAI. So you use OpenAI Python APIs. or if you want to go for Claude, or you want to go for something like, DeepSeek, whatever it is, So you're going to call APIs directly. Either you can directly call the APIs provided by those companies, or you can use a framework, or you can call it as a library, something like LangChain, for example, which is very popular here, for example, I'm saying. Or you can go for other options like chat LLM, for example. So one API can talk to all the different LLMs out there. But in short, people generally call the APIs and they send the request, they send the prompts. We call those prompts as input. So we send the prompts and then they receive the answers. So this is what you are going to get from them. So you send a prompt and what you get out of them is the answer. So this is the input and this is an output from that program. This is what we are doing when we say we are in AI or in ML, or we are AI engineers or we are ML engineers. So in short, you write the program in any different language out there. Could be Python, could be JavaScript, could be anything like C++ also. Essentially, you are calling the APIs and getting the answers from the LLM. So this is the major problem. Like you are kind of using LLMs like a black box. You do not know what happens behind the scene. If I'm sending a prompt, you don't know what a OpenAI is doing behind the scene so that it is kind of returning the answer. I mean, how is it possible for OpenAI or Claude or DeepSeek to answer your question? I mean, what goes beneath? No one knows that. This is the major problem. And when you see this kind of problem, when there is a problem, when you see the real challenge, if you want to debug something, you can't, because your knowledge is limited to only the prompts. And that's exactly what you can do. You keep on changing the prompt, you try going for something like a prompt engineering and something sort of that. I'm not saying prompt engineering is not a solution. Yes, to a certain extent it is. But when you are doing something which is really requiring the skills that you don't have, you are feeling short of this because you use it as a black box. So what we want to do right now is like we want to go inside it and find out how these guys are working, so that tomorrow if something is not working, I know, acha, that's the maybe the QKV, probably something is going on there. So that's why I'm not getting the answer here. No problem. I can just go back here and try to solve the problem by using the not the tricks, but by using the logic what these guys are using behind the scene. This is the major reason why we are stuck on sometimes facing the problems and we can't find a solution other than the prompt engineering. Another problem is like everyone is using ChatGPT today. I mean, everyone, just ask anyone, even if you're not into AI or even if you're not into ML, everyone knows ChatGPT because they literally put the questions and get the answers. But very, very, very few understand how it works behind the scene. This is what I'm again telling you one more time. Like, we are using it as a black box. We are not leveraging the power of ChatGPT because we just pass the input and get the output. We don't go beyond the limit. Almost no one can build one, and this is very true. Ask any person and just say, can you build your own LLM? I mean, building LLM is not a joke, I understand that, but I'm not saying like you have to build your own, but at least understand what is required to build one. Why is it important? Again, this gives you a knowledge that will, I mean, that you can use it to leverage for solving many different problems out there. And believe me, when you go into real AI or in ML engineering, solving the real world problems, you need to know more than LangChain. You need to know more than just using a ChatGPT or like LLM there. That's why we are looking for this one. Many people generally do not go into it because of they are having a fear of math. Believe me, you don't need any high quality or high understanding of math. It's even basic high school math is more than sufficient, And don't worry, we'll talk about that a little bit later. But high school math is more than sufficient for building your own LLM. Believe me that. And I'm going to prove that in next couple of days. There's a huge gap between the demo and production, and this is generally this is generally the case. When you go for any of the sessions or any of this one, like we are also having another course there where we generally talk about the LangChain. How do we use that? How do we write the code? How do we send a prompt? How do we get the answer and all of that stuff? But that's all to the demo level. When you go to the production, you are going to face a lot of different challenges. So these challenges cannot be overcome unless you know the internal knowledge of any of the LLMs out there. That's why we are looking for this one. Another big problem is a short-term skill without long-term benefit. Generally, when people want to learn AI, they want to learn a framework. This is the major problem. They want to learn a framework. They want to learn a programming language. They don't want to learn how it works. Why? Because how it works may not give you immediate benefit. Let me tell you this one more time. This course, once you understand, once you go through, might not give you the immediate benefit right away, but this is the long-term benefit that you are getting. Why? Tomorrow you might go for something else. Instead of using LangChain, you might go something else. But the things or the fundamentals and how these guys are working will never change. They will work the way they are working because they are following an architecture. This is what we're going to discuss today. You know, so basically, this is what we are facing the challenges today, and that's the reason why I thought of going for building one LLM from our scratch. I mean, our own LLM from scratch, so that you can understand there is no magic. I mean, OpenAI or Claude or any of the LLMs that you are using, it's not magical. It's not like they are kind of bringing some answer from somewhere else. They already are having it. But how would they answer the question? That is the secret we are going to reveal throughout this course. Again, we are going to go with the first principles, understanding the basics. Again, we are not going to use any of the APIs. I'm telling you this again. We are not going to use any API. We are not going to use any framework. It's pure math, pure programming. That's it. Nothing more than that. There's no magic. There is no API. We're just going to follow the first principles there. Okay. Now we'll talk more about what we are going to cover later. But before we go there, I want to answer a couple of questions, and that will benefit those who are attending today's and tomorrow's session as well. Only. So basically, when we talk about LLM, the LLM has something called as LM in it. That LM stands for something called as a language model. So let's answer this question. What do you mean by language model? So we can understand what do you mean by large language model? Because large, it's just like a language model, which is having a large data set. So if you can understand what is a language model, you can easily understand what is a large language model and how it works behind the scene. So a language model, it's a system. I mean, if you think about it, it's just a software, it's just an application, it's just a system that learns the patterns in a human language so that it can understand, predict, and generate a text. This is the major reason why language model exists. What it does? It learns the patterns. Please understand that. There is no magic. I mean, any of the models that you are using, they do not remember anything. They follow the patterns, and patterns are built on top of numbers, or you can call this as numeric data. So they look for the numeric data, they understand the patterns, and using these patterns they answer your question. How would they answer the question? They I'm kind of again highlighting this word understand. They do not understand. Let me tell you that this is generally called as a predictive model. I mean, so sorry, when I say understand, they do not understand anything. This is just a prediction. This is just a prediction. They do not understand this. I mean, in general, we say they understand, but they do not understand. It's just a prediction. It's called a predictive model. More on that later. This is again, using that understanding, they can predict the future values, or they can go for generating the text. This is what do they do. So language model is just a program which understand what you are going to pass by looking at the patterns inside that data and start using that pattern for predicting the future. That's it. Nothing more than that. So if I pass something like a hello to my code or to my LLM, for example, what it is going to predict is something like a word. That's it. This is the simplest thing LLM does. It generates the next word. This is called as next token generation. That's it. This is what LLM does. I mean, not LLM, to be honest, any language model out there, it can do the job. This is what it is meant for, generating the text. That's it. So in short, given some text, like what I said here, given a text like a hello, in this particular case, what is the job of LM? A job of LM is to predict what comes next. So hello world, machine learning, artificial intelligence. It is going to predict the next word. That's it. Sometimes the word really works well, sometimes it does not. Again, why it does not? I'll answer that question a little bit later. What do you mean by temperature, or how that KV cache works, or how that KQV generally generates the values or generate the next word by using a softmax function, all of that stuff. We'll see what do you mean by that and how we'll solve the problem, how the learning rate is going to affect that word generation, all of that stuff. We'll see step by step, gradually. But in a nutshell, a language model's main job is to accept something and generate next thing. That's it. This is what we call it as next token generation. More on the token in a second. So it does not truly understand like what human does, or it does not know the facts internally as well. This is the myth. We say like ChatGPT knows everything. No, it does not. I mean, Claude can answer any damn thing. No, it does not. It understand means it looks for the patterns. Nothing like that. I mean, we don't have the human cognitive thinking inside the machine yet. I mean, I'm saying yet. In future, it might be, but right now, it's not. It is just looking at the patterns in the numeric data and solving your problem of text generation. That's what the language model is used for. Again, a language model is a probability machine. This is what I said. It's a probability machine, nothing more than that. It is a probability machine. It's not going to understand anything. It is not going to remember anything. It is just a probability machine. What it does, it is getting trained on the text that predicts and generates the language by learning pattern in how the words appear together. If I feed the information, let's say hello, instead of saying world, if I say hello, hell, if I pass this information here, instead of generating hello world, it will generate the hello hell. Why? Because this is what I trained that LLM to do. So basically, it looks for the pattern, nothing more than that. Nothing more than that. One interesting example I'll show you later is like, how do we come up with names of the people? I'll feed almost like 100,000 such names to my LLM, and that LLM will understand the patterns, how the characters are kind of arranged in a particular form, and then it will start bringing, the new innovative names to the people. Let's say, for example, there's a newborn baby, and I will just go for a naming ceremony. I don't know what name I can go. I mean, what should I give name to that kid or to that baby? So I can use that program, and it will generate maybe a couple of dozen names for me, an innovative names for me. This is possible because it is going to understand, acha, after O there is a space, after space there is a H, after H there is an E, there is an L, there is an L, so on and so forth. So it will try to understand the patterns every now and then, and using that pattern, it is going to generate the text. That's it, nothing more than that. So what do they do? I mean, generally, when you talk about the LM, the language models, what are they famous for? They are famous for only one thing, text generation. But using the text generation logic, this is the main job. But using the text generation logic, or while passing the data, if I pass a huge amount of data to this model, something like this, this is the data we are kind of using. And this data is a huge one. Maybe I can say huge data. And if I pass to that model, this is my model. And if I train that model shows intermittent behaviors. These are the behaviors which we can leverage to solve other problems as well. Our main problem that is getting solved by language model is to text generation. But the same logic, the same data, the same text generation patterns can be used to leverage the other problems as well, like question answering, which is what the ChatGPT does, or translation from one language to another language, or summarization. I mean, you must have done that. Passing the document, you can say, hey, summarize the document and pass it to me, or summarize this email and just give me the gist of it. It does that job pretty well because it can understand the patterns inside it. That's the reason. Of course, chatbots, the best example that we are using today, code completion. I don't have to tell you vibe coding. What does it mean there? Code completion, and reasoning. To some extent, reasoning is still new in the market. I mean, not all of them are still kind of going with the reasoning, but still, reasoning is also to some extent is possible by using large language. So before I go further and talk about what is a large language model, may I know, guys, if you understand what is a large language, or not large language, but what is a language model here? Simple yes, no, thumbs up, thumbs down will help me to understand whether you are there and whether you are getting it. I'm going a little bit slow, because there are so many concepts. I want you to digest slowly, gradually. Then only you will appreciate what these guys are doing, or how the chat GPT or something like, these programs work behind the scene. Okay, I can see a couple of them saying yes. Reasoning and deep thinking is the same. It's a kind of Divakar. There is something as a chain of thought, and there is something as a mixture of expert, MOE and COT it is known as. So to a certain extent, these are same, but there are a few differences. I'll talk about that when we go for causal attention model. In attention model, later in transformers, we are having three types of attention models. One of them is called the causal self-attention model. And there I'll answer the question. What do you mean by reasoning and what do you mean by deep thinking? Well, till the time, I'm going to put your question on hold. But I already have answered it to a certain extent. They are similar. But there are quite differences as well, which we are going to clarify there. Okay? Fine. So let us understand what are the different types of language models are available. I mean, the one that you can leverage or the one that you can see in the real world. One of the simplest types of language models are something called the statistical language models. No one uses them. Now I'm saying, though they were getting used earlier when when there was RNN, when there was NLP, which was the only options available at that time. These people were using these statistical language models, which, for example, can be n-gram model. Like for example, were something called as a bigram or trigram. So unigram, for example. These are very simple examples. I think tomorrow when we go for tokenization, I'll talk about this example, like what do you mean by n-gram solution or how that n-gram really works, operating one character by character option. This is the very simple and simplest option when you go for language model, n-gram model. It can also be based on the word frequency count. This is generally called as a bag of words you might have heard about. Limited context window. This is not something we'll be using today, but this was the, we can say the history, I can say. Earlier, people were using this. For example, these kind of language models could be predicting only 2 or 3 words, not like the entire essay or nothing more than that. It's just like a very limited capability model. This is not something we are using today. This was something we were using earlier before using transformers. So this is called a statistical language model. Another one is like a neural language model. Neural language means they are kind of built by using neural networks. Something like RNN, for example, LSTM, GRU, for example, transformers, so on and so forth. They learn the meaning of the words. Here, the meaning of the words was not possible. So, for example, if I say I deposited, let's say, $100,000 in a bank, statement number one, and statement number two, I am tired and I'm sitting beside a river bank. If you see, there are two statements having the same word bank, but both of them are having totally different meaning. You know, in first statement, the bank, I'm talking about an institutional financial institution, while in the second example, I'm talking about the river bank. It's like the side of a river. So in this particular case, when we go for statistical language model, they don't understand the meaning of it. They just go for converting one to another and just keep on generating the character or word, nothing more than that. But when you go for something called the word embeddings, there are different algorithms out there, something like a word to vec, glove. I mean, these are pretty simple ones. These are also static embeddings, but there are more like BERT, for example, which is very famous, bidirectional encoding transform representational transformers, which is very popular embedding technique used for understanding the meaning of it, like king and man. I think they are kind of similar. Apple and banana, they are similar, but king and apple, those are two different things. So how would they find the relationship? We'll talk more into it in the day after tomorrow session. Something when we go for vectors, we'll understand what do you mean by vectors, or how the vectors are drawn. What do you mean by finding similarities of it, or how you can go for something as a vector maths, like what do you mean by superimposing vectors, or how do we find the cosine similarity, why it is similarity can be found by using dot products, or why dot products, or how dot product works. All of these things we'll see later, but this is what you are going to find inside the word embeddings, and this is when we have to go for leveraging something called as neural networks. This is creating a language model by using neural network. I mean, here the data is quite huge. You can't handle that data. You can't bear that data with a statistical model. And that's where we are going for neural networks out there, right? Yep. So in this particular course, we will be talking about how do we write our embedding model tomorrow only. I mean, yeah, even if you're not joining the course, it's fine. But tomorrow you are going to see like how this embeddings really work. I'll show you a small example of how to create your own embedding model. So to understand like what exactly the word to wake or glow are doing behind the scene. We can generalize better than the n-gram. That's the reason why we are kind of going for something called as a neural network. Another one, and which is what we are using today, they are called as a transformer based language models. So before transformers, they were using neural network. Most of them were using, I mean, they started using RNN, then they used something called the LSTM, and then towards the end of this era, they settled with the GRU, but they were having many problems. One of them is like vanishing gradient problem or exploding gradient problems, having a having a small window, or they would be forgetful, generally called as. And that is the reason why they thought of in 2017, Vaswani, the person who is behind that a very revolutionary paper, Attention is All You Need. They have come up with an idea called the transformer encoder and decoder architecture. Next week we'll talk more about transformer, the in detail understanding of transformer. Like, what do you mean by the encoder? What do you mean by decoder? How do we write our own encoder or decoder? How does the encoder and decoder work behind the scene? I mean, literally from scratch, we'll see and we'll write our three types of transformers. I mean, encoder only, and decoder only, and encoder decoder. All of them will be writing from scratch next week. Anyways, so this is what we are talking about today, modern LLMs. We are kind of using the transformers behind the scene. Most of them, I'm not saying all of them, but more than 99% of the LLMs today, we are using transformer based. They use the attention mechanism, attention mechanism, self-attention mechanism, and causal attention mechanism, and then multi-head attention mechanism. So there are four different ways. We'll see like how do we implement them in the transformers. But that's a core part. It's like a heart of any LLM called the transformer, and heart of transformer is the attention mechanism. Very famous, sometimes difficult to understand, but we'll see. What do you mean by KQE? Vectors, and how does this really work behind the scene? But that's what that drives the whole LLM, attention mechanism. And why it is so popular? Because of this attention mechanism. It handles a long context. This was the major problem in earlier versions. Like, they were not able to handle they were not able to get a long context because of the short term. It's called LSTM, long short term memory. That's the reason they could not handle the long context, and because of that, the gradients were getting vanished. That's what we generally call as vanishing gradient problem. More on that later. They power today's AI assistants. I mean, all of those LLMs that you are using today. Like, for example, you're going for GPT, you're going for Claude, you're going for DeepSeek. There are many different LLMs out there. Most of them are using transformers behind the scene. What do they do? What are the capabilities of them? They can answer any questions because they can understand the patterns, so on and so forth. Summarize the text, translate the language, write the code, and whatnot. I mean, whatever that I mentioned here, all of these can be fulfilled by using today's modern LLMs, which are based on something called the transformer. And transformer is based on attention mechanism. That's a core part of your LLM out there, which is what we are going to code in next week. Anyways, so now you know what LM is, what language model is. You understood what are the different types of them. Now let's understand, or let's add L into it. So probably that L here, it stands for large. So now we can answer the question, what exactly a large language model is. What is a language model again? A language model is the system which, if you pass some input text, it is going to generate an output text, or it is going to predict the next word what you have passed previously. Now, why then we go for a large language model? I mean, if the language model was anyways kind of doing the job, then why do we want to go for a large language model? I mean, what exactly the large here in that language model is? Let's see here. What is the meaning of large language model in this case? A large language model, or LLM, is a language model. Again, it is a language model trained on massive amount of text with a very large neural network, enabling it to perform many language tasks without task-specific training. Now, there are many things in this entire definition. Let's kind of cut it down in a small pieces and try to understand piece by piece. Number one, when you talk about this, we said that multiple times, it is a language model, which means there is a pattern. Using that pattern, it generates the next text in a nutshell. Okay. To create this model, we are looking for massive amount of text. When I say massive amount of, the last one, I think GPT 2.0, I mean, at that time, they used few trillion tokens to create the model. You can understand trillion models, trillion tokens. So probably it's around, around few terabytes of data that they have used. Almost half of the internet they have used to create the GPT-2. I'm not talking about GPT 5.2. I'm talking about GPT-2 at that time. So they have used a massive amount of text. Why do you think like we need a massive amount of text? The reason is very simple. If I give only two words like last time, hello hell and hello world, probably it can just understand hello. After hello, it could be like world or hell. But when you are going in the real world, there are n number of words out there. There are n number of possibilities out there. So to understand the possibilities, we have to have a massive amount of text. And that's exactly what large language model is leveraging here. So they are using not terabytes. I think it's exabytes of data that they're using for training the model. It's a massive amount of text. But when you have this amount of text, you can't go with something like a very simple example of, LSTM or GRU. You have to go for a little bit, better transformer based models, which are leveraging again the large neural network. That is where the distributed nature comes into picture. That is where we are going to have the neural network with not thousands, but millions of neurons. And that's why I think you must have seen that. ChatGPT, let's say 5.2, they are having a trillion trillion parameters. What do you mean by parameters? The parameters are nothing but combinations of weights and biases. So in that particular case, they are using a huge neural network, and on top of it, they are putting up massive amount of text to create this large language model. Now, when you are having such a massive text and you already have learned something out of it, what can you achieve? You want to achieve many different tasks, but very important, without a task specific training. In a sense, when I'm having a too much, words knowledge, I can ask any damn question and can answer the question. Like for example, I can say, can you translate that? Now, because it already has learned it from, so many data sources, it can easily translate your word. If I say, summarize it. It already has learned so many words out there, massive amount of text. It can also do that job. I can ask the question and get the answers, question answering, text generation. I mean, just name it. GPTs, not GPT, I would say, but LLMs can do it because they have learned these patterns from massive amount of text. And that's the reason why they can solve these problems. And that's the reason why we are using them in the first place, right? So when you say large language model, the large in the LLM refers to number one is the massive model size. I mean, of course, if you think about the parameters, today we are not even playing with the millions. We are either playing with the billions or trillions now. If you go for Llama 4.1, they are using trillion tokens, trillion parameters. So this is very important to know. More the parameters that you are having, more the accuracy it is going to generate. So again, more on that later. What is the parameter and how do we use it there, or how do we leverage it there? But at the moment, you can say the model size is not in maybe KBs or MBs. It's in GBs. So model size is massive. They are using a large training data, a massive training data, like books, code, web pages, papers, and so on and so forth. You just name it. They have already have used it while training the data. And they are using a huge compute power, huge. I mean, they are using GPUs, TPUs, NPUs, distributed training, and so on and so forth. So you just understand, like, those LLMs are built on massive amount of data, massive amount of text. And to use this text, they have to, to process this text, they have to go for GPUs, TPUs, and whatnot. I mean, they are leveraging all the compute powers that we are having today. So what are the key characteristics of them? Number one, as I mentioned last time, most of the LLMs that we are using today, they are called as modern LLMs. They are transformer based. And that's the reason why I said transformer is the core part of any LLM today. It's like a heart of any LLM today. So almost all LLMs are using transformer architecture. More on that next week. We will be writing our own transformer from scratch next week. Heavy use of self-attention to capture the long-range context. Again, we'll be writing both transformer as well as self-attention mechanism from scratch just by using Python and of course the math, not more than that. We're not going to use any API. We'll be directly using PyTorch, and using PyTorch, we'll be developing everything from scratch. But again, as I said, this is the core part of any LLM or the heart of any LLM. It's like the they are transformer based. Most of them or all of them, if you are going for LM today, they are pre-trained and then adapted. In a sense, you already have got those pre-trained, they already have got the foundational model, and on top of that, they have put the instructions, they already have got trained, and now you are going to adapt them to solve your own problem. So they are first trained on the general text, which is called the pre-training. This is called the foundational model. More on that in later case. We can call them as foundational model. And this foundational model is what we are kind of using further to train or to go for instructions. This is called the instruction model. Later adapted using fine tuning or instruction tuning and reinforcement learning from human feedback, which is called as the RLHF. More on that next week, I believe. I think next to next week or maybe the last week. RLHF, reinforcement learning with the human feedback. This is the most important thing to fine tune our model. More on that later. And finally, they are used for general purpose. I mean, they can solve many different problems out there. One single model can answer the question, or write the essays, or generate the code, or translate the languages, summarize the documents, or there are many different things it can do. I mean, you understand what kind of problems that you are solving by using LLMs today. Almost all. So probably when you are talking about the LLMs, there are many characteristics, but major characteristic is this. Most of them are transformer based. For example, there are many again, GPT series, all GPT-2, 3, 4, 5, 5.2, whatever it is. BERT, very important. We are going to bring that in tomorrow's session and we'll see like how the BERT works. Not the entire architecture, but at least to a certain part of it. Llama, very important from Meta. Gemini from Google and Claude from Anthropic. And there are many, many, many more LLMs out there. I hope you understand what we are saying here. Chetan, it can understand the images and video as well and generate the images and edits. On which data it has been trained, or how does it process images? Wonderful. Good question, Chetan. When we are going for something like this, let's say images or something, as I mentioned, it could be a text. Let me make it very generic. Let's say this is a text data, or maybe I can say this is the data, whatever it is. It could be a textual data, it could be images, it could be audio, or it could be video. Whatever data that you are having, it could be structured as well. This is my massive data. This data you as a human can understand, but machine cannot. And that's the reason this goes and this undergoes something like conversion. So this all get converted into numbers, or you can call this as a numeric data, and then you are going to pass it to your model. I mean, how does it work? This is the answer we are going to find out in tomorrow's session, where this part here, or this part here, I can say, is called as tokenization. Or after that, we go for something called as embeddings. Most often, when we are going for textual, there it makes sense to go for tokenizing or embedding. But when it comes to like images, audio, or video, we don't go for tokenization like the way we go for text. For them, let me switch it back and say this way. So for this, the text, we go for something like the tokenization or embedding. For rest of them, we generally go for something like CNN architecture, where they all get converted to something called as the pixel level, and the pixel get converted into numeric or numbers. So in short, Chetan, doesn't matter whether you are kind of using images, video, audio. Ultimately, everything has to get converted into numbers. Either you go through this path or you go through this path. This is what we are going to explain tomorrow, not images and audio video, but for textual part, we are going to explore tokenization. We are going to start exploring tokenization in tomorrow's session. Okay. Nitin, why is it called as adapted instead of fine-tune? There are reasons. When I say fine-tune means you are kind of you are kind of giving your own data, and then you are kind of making that model to understand that data and then use it. When I say adapted, that means the model, the same model, without giving any of the data, we can use it for, let's say, classification, text generation, or something sort of some other techniques as well, by giving some kind of prompts. So by using prompts, we are kind of adapting them to solve our problems. Fine tuning is also one of the options, but when I say fine tuning, it has a different meaning. More on that in the last week of this entire course. But in this case, we are using adapted word because we are not fine tuning it at the moment. We are just using it and solving our problem. If you are giving a new data and then we are asking, now learn from this data and try to solve this problem, this becomes a fine tuning. That's not adaptation. It's called the fine tuning of your model. A small difference, but it makes a lot of sense. Okay. In a small language model possible, yes. SLM and LLM, both of them are possible. Essentially, what we are saying, bring our or build our own LLM. It's not actually LLM. It's going to be like SLM, to be very honest, because we are not going to have that massive amount of data. Architecture remains same. The philosophy remains same. Methodology remains same. Logic remains same. But we don't have that much of data. So for our case, it's going to be a small language model. So LLM or SLM. What's the use case? When your data is not too big, we go for SLM. It's like conceptual part. If the data is massive, we call it as a large. If the data is small enough, we call it as SLM. Nothing more than that. I mean, this is nothing more changed here. Philosophy remains same, considerations remain same, architecture remains same. It's just data, which is kind of a little bit smaller. Nothing more than that. I don't know who that asked question here is, but user, whoever that person is, that's a difference. Okay. Hemant, when you are writing something, going out of screen. Okay, no problem. We'll try to. Yeah, pixel is going to be equals to feature map. Yes, Pranay, that's right. But LLM can't generate image, isn't it? No, it can't. I mean, sorry, it can, provided it has multimodal capabilities. So not all LLMs can generate the audio, video, not audio, but let's say images, because they don't have the training done. I mean, recently 5.2 can generate images as well. I'm talking about ChatGPT now. So the GPT can generate it because now they have learned on the multimodal capabilities. So it all depends on the capabilities of the LLMs out there. There are some vision models, they can generate the images, but those not vision models, they can't. So it depends on the LLM that you are using. Akash, do they store the numbers and data, and where? Uh, do they store numbers and data? Yes, do I mean they do store the numbers and data, and how, where, in terms of something called as weights and biases. More on that later. Okay. Now I think better we can continue further, and let me take a couple of questions again. Okay. Just last one question. I guess the adaptation is used because it's called the first principle model. Yeah, I mean, one of the answers is yes. Uh, we are building LLM to solve the particular problem statement, or we can say that we are building SLM. To be honest, yes, we are building SLM, as I mentioned, because our data is not that huge, but the concepts remain same. When you say SLM or LLM, the concept remains same. It's just the data. When you are having a huge amount of data, we call it as a LLM. When the data is very small, we may call it as SLM. Conceptually, it's just the same. It's just like data, which is going to differ. Okay. Okay, now we understand what is LLM. Let us go for what exactly LLM is not. So you can see like what is the ground truth here. LLM is not an intelligent human. You can't replace. I mean, you can't replace human with LLM out there. It can't. It is not a source of absolute truth. Why? I mean, have you not seen that? It is not knowing many facts, so it does not know the facts. They reproduce the patterns. I mean, if you ask the question like, who's the president of, let's say, US, for example, it can give the answer today because the Donald Trump is the answer, and they know that part. I mean, if you ask the question, maybe let's say, if you would have asked the same question maybe a couple of years before, it wouldn't have answered the question, because at that time the model was not knowing who's the current president of that. So precisely they do not know the facts, the real facts, because they don't have any access to the internet. So it's not possible for them to remember everything or to know everything. So whatever that they have trained on, they can remember that. They can confidently give the wrong answer. I love it. They confidently give the wrong answers, which we generally call it as hallucination. They get hallucinated, you know, because of the training date, or you can say training limit, or because not having the facts. They definitely and confidently give the wrong answer. This is what we generally call as an hallucination. They don't build in the fact checking. Whatever that fact that they are having, they just throw it out. They don't understand, or they don't want to cross check it with the real world. They don't do it. Knowledge may get outdated, and these are the major reasons, all of the reasons because behind the hallucination. So they are not absolute source of truth. Whatever they know, they are going to answer the question. There is no not a reasoning engine, which is by default they are not reasoning engine. I mean, they have to code for that. Again, this is different altogether. LM don't reason like the logic engineers or logic engines, like, or human. So they don't have the reasoning capability, at least to not all the LMs. There are a few they are having it, but not to the certain extent what human can do. Reasoning is again pattern imitation. So they do not have the reasoning capabilities like we human can have. They are just going to find out the pattern and work on that. Nothing more than that. They can fail at the multi-step logic, math proofs, symbolic reasoning, and so on and so forth. So it's not like all the problems can be solved by LLM. You can't. You can't expect LLM to solve all the problems till the date. And of course, they appear to reason because such pattern exists in the training data. So everything depends on the training data. If the training data has a pattern, it can imitate it. If it is not, it will say, I don't know. They are not the databases or the search engine. So they do not store the documents. They do not, I mean, we can't search into the LLM. That's not like they are database or search engine. They are not a deterministic system. Precisely what you are going to pass here, we call it a prompt. You never will get the same output all the time, you know, and output may differ because it's going to take different path all the time. And different neurons get activated, different output will get generated, and this is totally fine and this is totally expected. When you pass the same input, you never will get the output. It's not deterministic. Like, for example, tomorrow if I write a Python program to check if the number is prime or not, if I pass 10, it will always say it's not a prime number. No. So in this particular case, if I pass a prompt, it may generate one text one time and completely different text another time. It is possible, and this is what you already have seen it. So it's not a deterministic system at all. They use a probability sampling. More on that day after tomorrow session. Output varies from temperature and top K and top P. Next week, we'll talk about that temperature building. I mean, how the temperature works behind the scene and how that top K and top P really work. I mean, top K or top P work. That's like a solution to avoid repetition of the characters or repetition of the word. More on that later. Or to make it more creative. Again, just a formula. We'll see that in the next week. It's not guaranteeing the repeatability unless it is constrained. So probably you can understand it's not a deterministic system. It's not a memory system. I mean, it's not like it remember every single thing. It does not remember the past conversation unless it is expected to, I mean, expected or it is explicitly designed to do. One thing I want you to understand this point. If you are using ChatGPT, ChatGPT understand that. I hope you know and you already have used it at least once. So when you are using ChatGPT, ChatGPT remembers everything. And now I'm saying here, it does not remember the past conversation. How is it possible? I'm not talking about ChatGPT, guys. I'm talking about something like the GPT. GPT is the model behind it. Generative pre-trained transformers. GPT is the model behind the ChatGPT. ChatGPT, think about it as an agent which talks to the GPT and get the answer. So GPT, which is an LLM, it's not going to remember anything. I mean, it does not remember the past context, past conversation. It does not do anything. What you are going to pass to this, I mean, let's say ChatGPT system or agent, it understands, I mean, it has a memory, and within that memory, it knows what was the past conversation, and that conversation gets passed to every single time to the GPT, and that's why GPT can answer the question, remember in the past conversation. GPT itself has no capability to do that. It's not a world model, it's not a word model with grounding. In a sense, the LLMs do not have the real world experience. They don't understand anything in the real world. To be very honest, they don't have access to internet or access to the real world as well. They never see, they never hear, they never act like the multimodal extension. So unless it is, but otherwise they don't. And it's not a replacement of a domain expert. We as a human still are required in the companies. So you cannot replace a human with LLM. So LLM can do or can solve these problems, no doubt in that. But they can't do many things as well. They can't replace human at the moment, just because they can't think, they can't have the reasoning power of human. Of course they are heading towards it, but they are not. Okay, so today when I say the LLM, the first thing that comes to the mind is like the transformer based, and we already have seen like what is the LLM and what is the LM. Like, what if I want to build my own? How does it work? Let's understand the architecture of LLM very quickly, maybe 30,000 feet overview. Not like we are going to go in details of it, but just giving you an idea about it, like what you can expect in upcoming weeks out there. So in a nutshell, when you talk about any LLM, I'm using the word LLM here. So it is applied to every one of them. It could be GPT, it could be something like Claude, it could be any damn thing, DeepSeek or something. More or less, few things will change, but overall philosophy will remain same. Depends again on whether it has an encoder or it's a decoder only. I mean, it depends actually, but most of the things what we are discussing right now, they will be staying with all the LLMs out there. All LLMs out there. So generally, when you talk about something like the LLM, we start giving the input text. This is while training the data. I'm talking about training a model. Okay. So here we are, and we want to train the model. So this is training the LLM. So if you want to start training the LLM, we have to pass the input data. And this input data will will pass or will move it through a process called as tokenization. Now, this is the process which is going to convert it into number of tokens. More on that in a minute. I'm just giving you a 30,000 feet overview. This is like it is going through tokens, and these tokens could be something like characters, very simple, or words, again bit simpler, or subwords, bit complicated. We will be exploring this possibility tomorrow. It's called the byte pair encoding, known as it's called as BPE, byte pair encoding, and this is where we want to go for subword tokenization. Tomorrow we'll see that. But this is what it does. It is where it is going to convert all the probably you can say input text into small tokens. Tokens can be characters, can be words, can be subwords. Depends again on what kind of tokenizer you are using. Without tokenizer, none of the LLMs work. So tokenizer is the starting point. The tokenization converts every text into the tokens, and those tokens will get converted into something called as token embeddings. Now, what's a token embedding? A token embedding is just a kind of embedding vector. More on that in tomorrow and day after tomorrow session. Embedding vectors. So what do you mean by the vectors? I'll talk about that little bit, I think, in tomorrow's second part, or maybe I can say day after tomorrow's first part, where we will talk about what is a vector and how does it look like. In essential, or maybe in a nutshell, a vector is just bunch of values. It's called an array of values. I mean, array of similar values, to be honest. More on that later. I mean, directional vectors and non-directional vectors. We'll see that later. Now, once you are having the token embedding, you want to understand where in the sentence the word is kind of placed. This is called as a positional encoding. Let me give you a small example of it. Think about this. I'm making a statement. Boy goes to school. Now, when I say boy goes to school, let me just write it here so you can understand what do you mean by this. Let's say boy goes to school. A very simple example. Let's understand each one of those are tokens. This is the word tokenizer I'm going for. And this word tokenizer is kind of tokenizing my sentence into number of words. So these are my tokens. This is my token T1. This is my token T2. This is my token T3. And this is my token T4. Right? So this is my token. So whenever I can say this is my kind of a word, I'll call this as a token. Now, this will get converted into a, let's say, number. Embedding is just a number for us at the moment. So this is where I can say 1, 2, 3. This is 2, 3, 4. This is 4, 5, 6. And this one here is 6, 7, 8. Just a random number I'm choosing here to represent those numbers or to represent those words. Now, let us see the problem here. Now, this is what I have kind of come up with. This is like my tokenizer, which has converted that word into the kind of a token, and those token got converted into embeddings. These are my embeddings for now. I'm not converting them into vectors right now, but this is called as an embedding. Okay. Now, let me go for another example. Let's say school goes to boy. I know this is a completely messed up sentence, but let us see the problem and let us see what do you mean by the positional encoding, so you can understand what it is going to do. So in this sentence also, I'm having 4 same words. So it means like if I go back and convert this, this is my T1, this is my T2, this is my T3, and this is my T4. So we are having 4 tokens. And again, whenever there is a school, you're going to get the same answer back. It's like 6, 7, 8, which is what I saw here. So this is my school's embedding, same number. When you pass the same word, you always get the same number. Next one, goes. Goes is like 2, 3, 4. Then you go for 2. 2 is 4, 5, 6. And boy is like 1, 2, 3. Now, if you could understand something, whenever I'm passing the same word to the embedding model, or you can say maybe the model which is going to generate the embeddings, it is always going to give me the same word back, or same embedding back, or same number back. Now with this, can you see that problem? With this, I can see the same numbers are being generated here, but the problem here is I'm not able to understand which one of them is right, which one of them is wrong. I mean, both of them are having the same embeddings, same numbers, but one of them is wrong, semantically wrong, grammatically wrong, but one of them is semantically correct. How do I know that? To know this, these numbers or these embeddings get another type of embedding, another type of, you can say, mathematical operation performed on top of it, known as a positional embedding. Positional embedding means along with this, they now will also get the position as well, so that when I say boy goes to school and school goes to boy, they will give me the different meanings. So basically, tokenizer tokenizes means splits your data, splits your input text into the tokens. Let's say word for now. Those tokens get converted into embeddings, and those embeddings later will get converted into vectors. Embeddings are the numbers. Later on, those embeddings will get converted into vectors. Vector is an array of numbers. More on that day after tomorrow. But this is what it does. To make more sense, we know where that word or where that token comes in that sentence. We add the positional encoding. This is something that we are going to explore in the next week, on the next Monday session, where we'll talk about how do we generate the embeddings, how do we go for positional embeddings, and how do we create the. I mean, this is like the prerequisite of how do we go for creating a transformer, embeddings and positional embedding. That's the first part of it. More on that later. Okay, once we are having that positional embedding, we'll go for creating something like a transformer decoder blocks. This is like a GPT style one that we are explaining right now. So this is like a GPT like LLM where we are going to have only decoder blocks. If it is BERT like, we will go for encoder blocks. If it is TFI like, we can go for both encoder and decoder blocks. More on that next week. But this is a kind of, you can say, the architecture, or you can say an overview of how LLM works. Again, we are going with the input text, going with the tokenization, going with token embedding plus positional encoding or positional embedding. Then we go for transformer decoder blocks. Now, when we go for N means we can go for multiple transformer blocks so that we can tackle multiple things at a time, like the grammar or maybe the sequence or multiple things or multiple attentions within that particular input data. That is why we are going to have multiple transformer blocks. One block will have self-attention mechanism, embeddings and everything there. This transformer output, we are going to pass through another very important and again very essential mathematical operation called as a linear or softmax. Most of them it is a softmax. What is more, I mean, what is the meaning of that? Next week we'll talk about it. I mean, we will be writing our own softmax function as well. It's a very simple one-line code. But again, this is very important for you to know what is a softmax function. It uses a dot product behind the scene. I mean, why dot product? I'll answer that after tomorrow's session, where we start talking about mathematical understanding of it. This is called as a dot product. In a nutshell, dot product is mainly used for finding out the similarities in vectors. How? After tomorrow, Wednesday, we'll talk about it. And finally, once it understands or once it goes through something like the dot product, it will try to give you the next token. This is called as a next token prediction. This is where we are kind of finding out the next token. This is how it generally works, in a nutshell. Let's go through it one by one very quickly so understand like what exactly do they do and how do they do that. Okay. Let me quickly see what kind of questions that you are having. So probably we can also answer them while we are talking about this. Uh, Divakar, ChatGPT is an agent which have the multi-model simultaneous. LLM generates a text, whereas the other models work on. No, not like that. I mean, ChatGPT is an agent which is going to pass all the requests to something like a model. So model here is GPT and agent here is ChatGPT. It is going to ask GPT. I mean, it is going to pass the input to the GPT, which is going to be in terms of prompts, and the GPT is going to generate everything for you. So agent, it just passes the input to the GPT, nothing more than that. Sushan, tokenizer generates the token embeddings in a deterministic way. Yes, they will do that in deterministic way only. Right, depends again on which tokenizer that you are using, but sorry, embedding technique that you are using, but they will do the job. Okay, for sure. Shashank, what's the difference between token and token embeddings? Token means the part, or you can say the word or subword, or you can say the character. While embedding, it's like the numeric representation of it. For example, this is a token, this is a sentence, this is a token, and this is an embedding. I hope that gives you the clarity, Shashank. Token is a chunk of data where the embedding is a mathematical representation of a data. Yes, Divakar, that is right. Just quick correction. Mathematical representation means numeric data. So this is a token, this is an embedding. I hope that gives you the clarity now, right? What is a cost function? Softmax? No, softmax is not a cost function. Cost functions are the ones which are used for calculating the difference between the expected value and the original value. It's called the observed value. It's like y minus y hat. That's a cost function. For example, MAE, called as mean absolute error, mean squared error, root mean squared error. These are all the cost functions available there. Okay. These are mainly used to find out how accurate your model has predicted the value based on the observed value. So that's a cost function. Softmax is not a cost function. Softmax is mostly giving you the next value generation. Kunal, how would we train the model? How large data is fed to the model as it does not store anything? It should like large time. Yes, when you are going for LLM, it's going to take large amount of data, which means it's going to take large amount of time. Sometimes not hours, sometimes days or weeks to generate the entire model. GPT model, they have taken almost like I think few weeks to generate their first model. So you understand like how much time it's going to take. Swapnil, how it will decide to create the token with the words or the word subwords token? It depends on which tokenizer that you are using and how that tokenizer tokenizes the data. More on that in tomorrow's session when we start writing our own tokenizer. Then it will give you the understanding of how that generation will happen. So generation again depends upon the tokenizer. That's what I said. Every LLM's accuracy depends upon what kind of tokenizer that they are using. And most of them, they are using something called as a BPE. It's called as a byte pair encoding or byte pair encoding tokenizer. This is called a tokenizer, and most of them are using BPE. Tomorrow we'll talk more on that. Omkar, what is a transformer and how understand in the layman's term? Think about transformer as an engine and LLM as a car. In layman's term, car without engine makes no sense, and engine on its own do not do anything. I mean, you can't sit on engine and travel, and you can't travel in a car without an engine. Both of them fulfill each other. So in layman's term, transformer is an engine and LLM is a car. Okay. So car uses this engine so that you can sit in it and you can drive in the sitting. Similarly, LLM works on the basis of transformers. Okay. More on that in next week. We'll talk mathematically what the transformers are and how do they work. Okay. For now, just understand this analogy: car and engine. Car is LLM and engine is transformer. Okay. Okay. So we are talking about how does it work, the sequential one by one that we just have seen an overview of it. Let's go a little bit, put a light on each one of them and see how does it work. So when you talk about tokenization, that's the first one of it. The model never sees the text. It can work only with the number simply because we are talking about artificial intelligence and we are talking about machine learning. But artificial intelligence and machine learning are the part of statistics, or they are extension to the statistics. And statistics is a part of mathematics, and mathematics does not work with text. That's the reason. Okay. So this is the word, for example, hello. In that case, we are talking about characters, for example, as a token. So H is going to get converted into 7, 4, 11, LL, 7, 11, 11, and something like O is 14. So this is a tokenization. It's character level tokenization. So tokens can be a character, token can be words, token can be subwords. When it is subwords, we generally go for advanced tokenizer technique called as BP, byte pair encoding. Tomorrow we will be implementing one, not to be a very complete, but a kind of a giving you a glimpse of it. The next one, when the tokenizer tokenizes all the tokens or tokenizes all the, maybe you can say the words or subwords or characters, we go for converting them into numbers. It's called the embeddings. So numerical vector representation of a data that captures the meaning, similarity, and relationship. This is the important difference between a simple numbers and the embeddings. I mean, embeddings are numbers, no doubt in that, but they capture the meaning of it. Like for example, I can say man and king and queen and let's say woman. Both of them are kind of going near. Like if maybe apple and banana, both of them are going near, but king and banana not going in near because they are not having anything in similar. That's what the embeddings are. They understand the meaning of it, and this is possible by using something called as similarity. They already have mentioned it here, but this is possible because of something called as the similarity based on the dot product. This is the key to the key to the solving the whole problem, dot product. It's called a dot similarity, and this dot product is based on something called as cosine similarity. More on that in when I think maybe it's Wednesday or Thursday. I think Thursday we'll talk about it. What do you mean by cosine similarity, and what do you mean by the dot products, and why it's important for you to know that. Anyways, so embeddings is like each number becomes a vector. As I mentioned, vector right now is like similar, I mean, the collection of similar values or array of similar values. More on that day after tomorrow, Monday, Wednesday. Embeddings encode with the semantic meaning and contextual usage, relationship, analogies, and so on and so forth. It understands that because it is how it is trained. And to do this, we are kind of using the algorithms like word to wake or glow. These are like the old generations, fasttext. The one that we are using today, it could be something like the neural network based. It's called a BERT, for example. It is using transform behind the scene. And this is an example of it. King minus man equals to woman, kind of nearly equals to a queen. So this is possible to understand the meaning of it, and that is the reason why we are going for using the embeddings. Not simple numbers, but they are the embeddings. And someone said that it is kind of deterministic. So if you pass the same one, you're going to get the same meaning. But that depends again on the context that you are going to pass through. Okay, now this is the engine of a car, transformer, as I mentioned. So before transformers, the model read one text at a time, one at a time, which was very slow. It was very forgetful and impossible to scale. When I say forgetful, that was the problem. This is called as a exploding gradients problem and vanishing gradient problem. Forgetful means vanishing gradient problem, to be honest. So that's the reason why they have invented transformer. Attention is all you need. 2017, the research paper created by Vaswani and team from Google. They have changed the entire world, and where they have introduced this architecture called as transformer. This is something called as encoder decoder architecture. Encoder decoder architecture. And this encoder decoder architecture is what we are going to write from scratch in next week, next Monday. Transformers are the neural network architectures that processes the sequence using the self-attention instead of recurrence, allowing models to understand the relationship between all tokens in parallel. This is possible by using something called as multi-head attention. Again, next week, we'll be implementing this from scratch, and not once, we'll be implementing it 3 times, simple attention, self-attention, and causal attention. We'll talk about that in the next week. So the multi-head attention. In simple terms, each word looks like each word looks every other word to decide what matters the most. This is called an attention. Again, this is what we are saying. Like for example, when I say I deposited, let's say 100 rupees in bank. So in that case, when I look at the word bank, how should I know whether this is the bank as a river bank or whether this bank as a financial institute like a bank? So when I use the word deposit, this word is very important, and this is what I need to pay attention to. This is what we are saying. Which word or words I need to pay attention to? This is found by using the attention model. This is what we are saying. Which word that matters a lot. So we will need to find it out, making transformers very fast, scalable, and powerful for language understanding and generation. And that's the reason why most of the LLMs today are using transformers behind the scene. This is what do they do? This is called as attention mechanism. And this is the one that I said earlier also. This is going to drive the entire transformer, and the transformer is driving the entire LLM. So the attention mechanism lets the model focus on the most relevant parts of the input while processing the token. This is the one that is going to kind of, probably in this particular case, like how does it work? How does it kind of go giving you the output, attention mechanism. Not all word equally important. Attention is the one which is going to higher word, so that the one that is very important. Like what I said, deposit is the word very important to understand the meaning of a bank. So it gives higher weight to that deposit, and then it understands the meaning of the bank, not as a river bank, but as a financial institute bank. And there are 3 types of attention mechanism: self-attention, masked attention or causal attention, and cross attention. Like attention to attain the tokens in the same sequence. Again, next week. Prevent token for future tokens, which is usually used in the GPT. It's called the causal attention, and this is how we are going to build our LLM with this particular part. And one sequence attains to another one. It's called the encoder decoder architecture. It's called the cross attention. Generally, TFI like model, they use this cross attention mechanism. Every token asks, what am I going to look for? This is called the query in terms of attention mechanism. Q, it is known as query. What can I do, or what do I contain? I mean, what's there inside me? For example, it's called the key, K, and what do I give? It's called the value or a V. These are the three vectors we'll be using, Q, K, V. Remember what I said last time? What is a KV cache and how you can implement it, or how you can, make the LLM speed faster by implementing KV cache. That was one of the questions. So what do you mean by this? I'll talk about that when we go for implementing one next week. But this is an important point in the transformer and in the attention model, that there we are going to implement three vectors, Q, K, and V. Query, key, and value, it is known as. This is what we are talking about, multi-rate attention. More on that in the next week. We'll go for understanding multiple parts or multiple meanings of the sentence at once, parallelly. So instead of using one attention, the transformer may use multiple attentions or multiple heads to focus on multiple aspects of the meaning simultaneously, parallelly. We can understand syntactical meaning of it, or semantic meaning of it, words input of it, maybe something like a subject word relationship of it, so on and so forth. So a single attention head can focus on a grammar, subject verb agreement, long term dependencies, so on and so forth. So we can do all of them at once. Multiple heads allows model to learn all of this at once, and that's the reason this is what we are going to use in our model as well, or in our LLM as well. So I think we'll do one thing while we are talking about this. We'll write a very small code. Again, do not try to understand everything at once. I know this is just to give you a demo of it, so you can understand like how is it, I mean, how simple it is if you understand like what you are doing and how much time it takes for us to generate a very, very, very tiny GPT here. This is what I mentioned here, how tiny GPT work. This is how we are going to create a very small tiny GPT right now. And then we'll see like what can we do later when we go for our own project. Okay. A very simple idea behind it. Let's see if we can. Why are you opening on this side? Yeah, coming on that one. Let's go back here, 2025. Oh, it's 2026 now. Okay, let's create a new directory called as work. What is that? Workshops. Yes. And within that, this is like build your own LLM. And right here, I'll go for day one. And inside day one, let's create a new directory called as a code. I'll share this everything later with you. Okay, here we are. And let's go for a very simple example of it. I'll call this as a tiny GPT. Okay. So it's not a GPT to be honest, but it is more or less going to do the similar job. So this is called as a tiny GPT.py. Okay, let's start with this. So I'm going to go back here and start with this. First thing first, again, do not understand each and every line of code. This is not important. This is not even expected in this session. This is just to give you an idea about it. So this is like import required packages. Sorry, import required packages, whatever that we are going to need here. Like the torch, this is the main package that we will be using now. Okay. So let's go for the first one. Now we will load the data. So we can say load the data. Data is nothing but the one that we are going to pass input to train our model. We are saying that there's a data.txt. So let's go back here and say data.txt. Inside the data.txt, I'll put something very simple like hello world, hello AI, or hello something like machine learning, something. Understand that this is the data that I want to train my model on. Okay. So that tomorrow if I pass H, so it should give me something similar to what it has learned from. It's like the GPT is going to do now. Okay. Let's see one by one again. So we have imported required packages. We have started reading the data. Now to read the data, to get the tokens, we have to go for tokenization, which is what we are going to convert every single character as a token. So maybe I can say, consider all the characters, or consider a character as a token. And this can be done easily. We are kind of converting every character. We are kind of reading the entire text. We are converting every text into a set of characters, every character out there. We are converting into a list of characters, all characters, whatever that present inside it, and we are going to sort them out. That's it. Which is what we are going to convert it here as a vocab size. Vocab size is like vocabulary. What you are having in the vocabulary. We are going for character-based tokenizer. That means one character becomes my we can say the token at the moment. Now we are going to write two functions, not two functions, but two dictionaries, I can say. S2I, it's like the string to integer and integer to string. This is like convert every character to integer and vice versa. Vice versa. So this is what we are doing here. You're converting every character to integer or integer to character. Why? I'll explain that in a second. So basically, whenever we are kind of having some data, let's say in this particular case, we are going with something like a HELLO. So what happens here is H will come here and it will get converted into the integer by using H2I and I2H. You see, enumerated characters, we are kind of getting that the index and something like the characters. More on that in tomorrow's session, because tomorrow we have to do it practically. It's like a tokenization. It's the simplest algorithm of a tokenization there. Now I'm going to write two separate functions. One is going to be like decode and encode. So encode means it's going to be going for encoding, means like whatever the character that we are kind of getting, we'll be converting them into the integers. And decoding means if I pass the integer, I would get the if I pass the integer, I would get the character back. For example, if I say print, what the heck is that? Print, what is the name of that? Let's say encoded version is going to be equals to, let's say, encode and pass hello. So if I pass hello and if I run this code, for example, what's the name of that? Tiny GPT. So if I go for it, what it does, if you can see here, hello, the H here is getting converted into 7, E here is getting converted into 5, maybe LL, both of them are 9, and O gets converted into 12. It's like very, very, very simple tokenizer that we have built here. This is encoding. And if I pass the same encoding back inside this one, it is going to convert it into a characters here. Very simple. I hope you understand that. It's a very simple character-based tokenization. Again, more on that later tomorrow. I'll talk about this in details, like what's the tokenization, how the tokenization work, what is an algorithm behind it, and we're going to write it from scratch again. This is just an overview of it. Okay, now whatever the data that we are going to get here, let's say convert the input data to something called as a tensor. What's a tensor? A tensor is a like array of values, but the only difference here is the array runs only on the CPU, tensor runs on GPU as well. So you can get the data or you can get the answers pretty fast because they're going to work on GPU. That's the reason. Okay, now we'll go for setting up the hyperparameters. Now I'm not going to explain all of the things today. As I mentioned, this is just to give you an overview of it. So this is like the hyperparameters. So first, like block size, then the batch size, how many data that you want to bring together, batch size. What is the embedding dimension? It's very small, 32. Later on, we'll go for 128 or 256 and so on and so forth. Number of attention heads, there are 4. Maybe I can say number of layers, 2 for now. Learning rate, it's very small. I think 1 into 10 raised to minus 4. It's like 0.00001. Epochs, I think we'll start with only 2 for 2000 for now. And temperature, do I need it? I'm going to skip it for now. Okay. We'll see like whether it's, and I think learning rate I'll go for a little bit lower to start with. We'll see if it is needed, we can modify that later. Now we'll go for generating the batch. Whatever the data that we are going to go for, we are going to get the batch size. The batch size right now is 16. So whatever data that we are having, characters, I'm just going to go for 16 batch. So this is like convert the data into different batches. Convert the data into batches. Okay, so this is like get a batch. Next, this is the most important part, and I am just going to copy paste today. I will explain every damn thing later because you do not understand this right now because we haven't discussed anything yet. This is where we are going for self-attention mechanism. So this is like the self-attention implementation, and this is what we will be doing it. Don't worry, I will explain every damn thing, every single line of the code, and we will be writing it from scratch. This is what I mentioned, k q v, they are the vectors. More on that later. Do not worry about this. This is not, I'm expecting you to understand this code just to see like what it's going to give me back. We are just going to give you a small demo of it. And that's the reason why am I copy pasting the code. Most often we will just write everything from scratch, in the class, building up step by step. Now, because the attention model, I'll have to use it somewhere. I'm going to go for a transformer block. This is what we are going to use as self-attention here. And then it is having a layer normalization. It's called as layer norm or normalization layer. Again, more on that there in the next week when we go for implementing our transformer. Sequential model. This is kind of neural network. FC, it is called as a fully connected network that we are going to use here. Okay. So probably we can have a self-attention model, and then that self-attention, we are using it right inside a transformer block. This is like one block of a transformer. So similarly, I think we said we are going to use how many blocks? 8 blocks. I think number of 8 is equals to 4. So let's see. This is the GPT class, which is what we are kind of using here. So this is the GPT example. Instead of saying mini, I can call it as a tiny. This is not even a mini. This is teeny tiny, GPT. This is the actual GPT class here. So this is the GPT implementation. It's a very small implementation. Again, do not worry about that. I'll explain each and every line of code later. Like this is an embedding, the one that I said last time. So probably this is the transformer block. We are using 4 of them, 4 hits, multi-hit attention model that we are using here, and so on and so forth. I think we have removed the temperature. We are not using it right now. So let's not worry about that right now. And this is the generation logic. So this is going to generate my block or generate my text character by character because it's like character tokenization that am I using right now. So let's go for creating that mini GPT or tiny GPT, it is called as now. Tiny GPT. So I can say create the model, and maybe I can say optimize it. It's called an optimizer. Optimize the model by using Adam. We are using Adam optimizer here. More on that later. Now we are going to go for multiple epochs to train it. So this is what we generally call it as a training module, or it's called as a training loop. So we are having number of epochs. I think we are having 2000, I believe. So that's a 2000 epochs we are using. And this loop is going to run 2000 times. Every after 200, we are going to see like what is the current loss. Lesser the loss, more will be the accuracy. That's how we can put it. And finally, this is where we are going to inference the model. Inference the model. That's it. This is a kind of a GPT that we are building up with very small, very teeny tiny data out there. Okay. So essentially, I'm going to ask the GPT that this is my word, this is my token, this is my character edge. Now you generate the rest of the words. How many? 50 characters is what I'm asking you to generate. Let's see what it is going to generate for me. Going back here and running this. This is going to train the model 2000 times. And you can see that, wow, look at that. The accuracy is increasing. My God, I can't believe this. Can you understand what has happened right now? When I pass H as my first token, it started predicting E, A, C, H, I, N, I, G. After G, there's a /N. Again, H, E, L, L, O, deep learning. My God, it has given a very nice output. Very nice output. So basically what we have done right now, just to give you kind of a context here, we have just created a very small GPT, tiny GPT, which has learned from my data. And when I asked, hey, now produce 50 characters after H, it has produced those 50 characters. Let me just go for maybe 100, or maybe I can say 1000, whatever. So this is going to write an essay now. I mean, 100 words is, or 100 characters is what am I looking for? I can see that the accuracy is very nice because the loss is very small. Ha ha ha. This time it fails. Can you see that? This is what I said last time. You can't expect the same output every single time. And why does it fail? I'll talk more on that next week when we go for our transformer by introducing the temperature and by adding more learning rate. Ha ha ha. It is fail. I mean, it's not failing to be honest. It's not a bug. It's not a failing. This is responding to the training. Last time it has got very well trained. This time it is not. It happens because of the training, and you can see that it is what it is kind of telling you. It started with 2.7. It started with 3.0. It started with 3.0290. So all of this thing, what we are saying here is like the text being generated. And how does it work? It works like this. We are kind of having the input data, we are tokenizing it by using the encode and decode mechanism, or the encode or decode functions out there. We are converting it to the something like a tensor. That tensor we are converting into the batches, small batches, by passing through the entire transformer. It's like a transformer block which uses a self-attention mechanism, which is what divided into KQV, like this one. And then we are kind of going through the sequential, it's called the FC, fully connected network. And then we'll go for creating our tiny GPT, which is what it is using all of this stuff, which we are going to build later one by one. I know none of these things must have made any sense to you. I know that, but don't worry about this. I just gave you an idea about how a LLM code looks like. This is really an LLM code. And believe me, this is LLM code. If I can pass huge amount of data, this will start generating a very good result. Very good result. Right now, I'm not worried about generating the data. I'm not generating the result. I'm just telling you what am I showing you here? It's really a very teeny tiny GPT model where you can have large amount of data. It will start generating the text one by one. I think you must have seen that. Though the accuracy is not very good because my data is very small at the moment and I've not optimized the training parameters. I'm not kind of fine-tune those training parameters right now. And that's the reason it's not giving me a very good result. HININ blah 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 blah. It kind of giving me some data. It's understanding a pattern, and that pattern is what it is repeating. This is just because I'm having a very 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 small and teeny tiny data. Okay. So this is a very simple example of it, and this is what we are going to implement later with all the different things which I just coded here from scratch. From scratch. Okay, fine. So in this particular case, I hope you must have at least seen how does that code look like. Again, do not worry about this. Do not worry about this. This is just what we have started with. So if I look at what have we looked at right now in this particular session, in this particular today's lecture, let me just go through it. What have we covered? So what have we covered right now? We have covered what is LLM. We already have discussed that last time. It's a large language model which is capable of doing multiple different tasks like text generation, then question answer, and so on and so forth. What LLM can actually do, like next token generation prediction, I think I mentioned that. This is the only job of a language model. Generate the next token, nothing more than that. What LLMs do not do, or what they are not meant to do, is like thinking or reasoning like humans. They can't, as I mentioned last time. They just look at the probability of the next word, nothing more than that. Don't expect the GPTs or don't expect the LLMs to think or reason. They don't. They just look for more probability. That's it. Why LLM feel intelligent despite being probabilistic? It seems like it is thinking, but it is not, as I showed you earlier. And how ChatGPT, LLM, or all they share the same core idea. You go anywhere, and this is what you are going to see, the same idea, same philosophy is being used there. This is called as decoder only LLM. I mean, the architecture which I shared here, it's called a decoder only architecture. And this is what do that LLM like ChatGPT, Claude, any of them, they do this behind the scene. This is what we have covered today. But hold on, let me mention this. What have we not covered today? So today I purposefully did not talk any math behind a transformer. Rather, I didn't even talk about the transformer also line by line. I gave you just a small idea about it, like what a transformer code might look like. So we have not talked about the math behind transformer. We didn't talk about the matrices or the vectors, like what is the Q, K, V, what do you mean by dot product, what do you mean by softmax, how the gradient work, what do you mean by gradient descent, and all of that stuff. I didn't talk about that purposefully. We are not kind of expected to understand every single thing on day one, and it's not possible. Even if I want to, it's not possible. So right now, I just gave you a code, and that code is kind of, you can just say, it's like a copy pasted code in a sense. Like we have not really have written that code from scratch. It's like copy pasted code just to show you what exactly it can be. I mean, how does it look like and what it can do for you. You know, we didn't talk about efficient training techniques like optimizers. I mean, I used one, but I did not go and understand this from scratch. Learning rate schedules or regularization, didn't do anything like that. Learning rate, we used it, but it's not like we have understood it. We did not use the scaling models to millions or billions of parameters. I mean, we don't have that much of memory at the moment. We are not running it on the GPU right now. Later on, we will, and we did not use any distributed training. We just use a simple and single machine in order to get that simple data learn, and then we have used that knowledge to generate our next characters. Instruction tuning and alignment, we have not done that. We have not gone for instruction tuning. It's called instruction tuning, or it's kind of using the LLM for instruction model, generating an instruction model. We didn't do that. Why ChatGPT follows the instructions but the raw GPT does not? This is what we will talk about it later, like how the instruction modeling will be done. And in the next slide, I'll explain that in a moment. Fine tuning for the real world use cases, we didn't talk about that. We didn't use our domain data. We didn't use adapters. We didn't use LoRa and QLoRa, low rank adaptation, it's called as, and quantized low rank adaptation. We have not used that either. So this is not kind of, you can say, fine tuning the model. This is not what we have done today. We have not talked about retrieval augmented generation or RAG model. We are not connected to any of the private documents and databases yet, which will be doing it in the last week, where we'll talk about the use cases of LM, the one that we are going to produce here, and deployment of the production concerns like latency, like the cost, inference optimization, monitoring. None of them we have done now. So this is what we have not covered today. When are we going to cover that? Of course, that's what this course is for. We are going to cover all of these things in upcoming sessions. So basically, what are we going to do now? Now, in a sense, like what exactly this course is for? This course is for building LLM from scratch. And this is how we are going to split it into 4 different phases. Phase number 1, this is where we are going to build it's called the foundational model. So this is what we are going to do here. So this is the first step of it, build foundational model. This is what we are going to do, build a foundational model. I mean, what different things are required here? Number 1, this is where we are going to build a, maybe you can say the heart of it, foundational model. It's called as a very simple, which requires the data preparation. When I say data preparation, this is what I said, tokenization. And this is what we are going to start tomorrow. This is where we'll start tokenization. And we'll see multiple types of tokenizations like character tokenization, word tokenization, subword tokenization, byte pair encoding, and so on and so forth. So starting from tomorrow, we are going to go in deep, and then we are going to start exploring each of these blocks one by one. Once we are done with tokenization, the next part, of course, will come for, I mean, we'll have to go for is something called as the transformers. And when I say the transformers, there is the main part, the main logic called as attention mechanism. As I mentioned, there are 3 types of attention mechanism that we have to go for: simple attention, self-attention, and causal. We're not going for cross attention mechanism at this point. We're just going to go for simple attention. It's called as a without trainable weights, and we'll see the trainable weights, and then we'll go for self-attention, and then we'll go for causal self-attention. And this is what GPT uses behind the scene. Causal self-attention, it is known as attention mechanism. Then once we are having this ready and this ready, we are going to combine them together, and will create our first LLM architecture. This is our, maybe you can say, core idea. This is our class, which is kind of dream LLM. This is where it start taking the shape. Maybe next week, after 2 weeks, we'll start kind of working on this dream LLM. You know, this is our class that is going to build our model. I mean, to build this, we have to go for using the foundational model that I created here. As you can see, this is where I've created my foundational model. And this foundational model, I'm going to pass it to the next phase. This is my second phase. Once my architecture is kind of in place, I can go for the second phase where we can use this foundational model and start training the data. So this is like a training loop. When I say training loop, here I will use all the optimizers, or you can say something like the cost functions and so on and so forth, you know. So this is where I can go for optimizers plus cost functions and so on and so forth. So this is where we're going to train the model. Once the model is trained, we will evaluate it with different parameters like accuracy, for example, or we can go for F1 score and so on and so forth. Accuracy of your model. So we'll evaluate the model. And once it is done, I mean, once we understand, once we grab the idea, like what exactly it is, if possible and if required, we can use the pre-trained models or pre-trained weights, they are known as. So these are the pre-trained weights given by GPTs, and we will be using a GPT-2. GPT-2 pre-trained weights, or you can say GPT-2 weights. More on that later. So this will kind of convert a small dream LLM into GPT. You know, what does it mean? Hold on, we'll talk about that in the third week, third or maybe end of the third week or beginning of the fourth week. This is the foundational model. Now, this foundational model will not do anything other than next word generation. If I want that foundational model to do something like classify sentiment or something like a personal assistant, question answering here. So this can be fine-tuned to get this job done to go for a classifier and personal assistant. Classifier means it is like the classification. It's like the sentiment classification, to be honest. It's the sentiment classification. And the personal assistant means QA sessions. It's like a QA, question answering, it is known as, you know. And we have to build one. I mean, build in the sense fine tune one. So whatever that we have built, foundational model, we have to fine tune it to answer our questions. This is called as a question answering. And this is how your main GPT models are built. They have created the foundational model based on these things, and then they kind of fine tune it for a personal assistance. And that's why you can ask the question and you can get the answers from them. This is the path that we have to walk on for next maybe 4 to 5 weeks. You know? So this is what we will be building. Now, let me give you this little bit clear-cut idea. So all the questions that you are having right now, are we going to cover that, or do we have this one covered, and so on and so forth in this particular part here. So you will get all the questions answered here. As I mentioned, we'll start with the foundations, how the large language or LLMs really work. I mean, just now we started working on that. Tomorrow we'll talk about it again in more details. So what language models actually mean, like probabilities, not facts, and so on and so forth. We'll talk about tokens, embeddings, and so on and so forth. That's the first principle. That's the very basic, very, very, very basic. So this is where we'll understand, like, what do you mean by tokenizers and how do they work? Why math is needed and how little you actually need. We'll explain that in the foundations part. So as I said, you don't need PhD in mathematics. It's just simple mathematics, more than sufficient. Next, token prediction. We'll explain it deeply. Loss functions and what the models, why the model fails or repeat. Have you not seen that? In my output last time, in this particular case, if you have noticed, my model really, it did not fail actually. It tried to repeat the same story here again and again. Why did it fail? I'll mention that next week. Reading LLM outputs like an engineer and not a user. This is what my intention here is. You should start reading the research paper. You should start understanding the architecture diagram like a AI engineer, not like a user. User does not understand what's going there. User just call the API and get the LLM as a black box. We are not going to walk that path. We are just going to understand every single thing behind the scene. So here we will do the hands-on by building the different type of tokenizer, as I mentioned, vectors or matrix operation by using a PyTorch. Day after tomorrow, we'll talk more on that. What is an outcome of this? You will understand what LLM is doing internally and not the black box, as I mentioned. So this is just giving you a quick overview of like what exactly that LLM here is, but more on that will go next phases. This is the major part. I'll just put a star mark here because without this, No LLM work today. I mean, 99% LLMs do not work with them. This is like a more modern LLM we are talking about. Self-attention mechanism, KQV intuitive, as I mentioned last time. Positional encoding, I mean, why order matters and how do we understand what is an order there? Positional encoding it is called as. Feed forward network inside the transformer, it's called as an FC, fully connected network. Residual connection and layer normalization. I think in the code also I showed you layer norm. It's called as a normalization. Why is it needed? I'll talk more about that. Encoder versus decoder and why GPT is a decoder only. This is one of the classic questions in the interviews. If you are going for AI interviews, this is the classic question. Why GPT is decoder only? I mean, what's the reason behind it and how does it work? Very popular question in AI interviews. We'll answer that from the code as well. Causal masking and auto-regressive behavior. Auto-regressive means automatically, regressive means predicting the future values of it. In this case, we'll be building a transformer block from scratch using PyTorch only. PyTorch only. No other APIs are required. Only PyTorch. That's it. What is an outcome? You'll be able to read all the transformed diagrams and research paper with confidence. Yes, this is what my intention here is. I want you to understand the transformer from scratch. Anyone or anywhere going for any interview, and if there is a question on transformer, I can bet you will be able to understand. Sorry, you will be able to answer that question easily. That's what I can guarantee you after we finish the transformer next week. And this is something we'll be doing from scratch. So I can definitely bet on that. You will understand each and every character level coding there. Next part, training a large language model properly. In a sense, like once we understand a transformer, we are going to go for creating that class I mentioned, Dream LLM. So training the training loop in details or backpropagation with actual implementation of it. We want to go for, optimizations like stochastic grading the descendant or something like a Adam or Adam W, something like that. There are many others. Learning rate, why loss explodes or collapses. This is the problem here. My loss collapses, and that's the reason why it started repeating the patterns. More on that later. How do I solve the problem? Most often this problem can be solved by implementing something of the temperature, or we can improve, maybe reduce the learning rate. I mean, when I reduce the learning rate, it's going to take more time, but it may solve my problem. More on that later. Overfitting, underfitting, and data quality. All of these things we have to see in details. Why small models behave strangely with repetition and nonsense. I mean, this is exactly what you see here. Why this small model, it's kind of repetitive and nonsense. I mean, why does it do that? We'll understand that in this particular part, where we can train your own mini GPT model and debug its behavior. And this is exactly what we are going to do next week when we start building our own LLM from scratch. You will know why models behave badly and how to fix it. That's more important. This is an outcome of this entire part here. Next, we'll go for scaling, fine-tuning, and alignment. Another real-world challenge that we generally will have to solve. Why scaling works or pre-training versus fine-tuning? What's the difference between that? Instruction tuning. Why ChatGPT follow the instructions? Like how the instructions data need to be performed, or how the instruction data need to be created, curated. This is how we will see here. Parameter efficient fine tuning calls a PEFT, which is like a LoRa Q LoRa adapter, as I mentioned last time. When to fine tune and when not to. Another important question in interviews. Common mistakes in fine tuning, and this is where you will know the real companies how they customize their LLMs. This is how we will be doing our own. And the last section, once the LLM is built, we'll start deploying it and kind of checking it as an API. I mean, not like API of others, API for our own LLM. Inference versus training, we'll see what does it mean. Latency, cost, memory, trade-offs, model quantization, optimization, of course, high-level implementation of it. API versus self-hosted model. So both of them, self-hosted models will give you the answers directly, but if you are kind of installing it or running it on different, how do we make it behind the APIs? By using, I think we'll go for Flask. So by using Flask, we can make it behind the APIs, like what the ChatGPT you are using today. So if you have used the ChatGPT APIs, how does it work? Exactly the same fashion we'll be using our Dream LLM APIs. So anyone can call our APIs and get the answers there. Monitoring LLM outputs, yes, very important. Ethics, safety and responsible AI. I think you might have heard about guardrails. So this is where we are going to talk about it. Safetiness, guardrails, it is known as. And how do we stay relevant as model evolve? So which means fine tuning the models every single time. This is what we are going to see. What will you get? You will know how to take the LLM from a notebook to production. And this is a very important point. People generally do not go beyond notebooks, you know. So that's the reason why this is the last step in our entire course. And this is like what we are going to see in the last week. Like we will put this in AWS and we'll start using that from our application or from our machine. So it's like we are going to put it in a production environment there. So this is what the last piece of the puzzle will solve in this particular course. Okay, again, what exactly we'll be writing here? I mean, there are so many codes. This is what the list of programs that we'll be writing. Tokenizer, embeddings, attention and transformer internals, transformer architecture, language model, fine-tuning and adapters, and again, a RAG, a deployment and engineering, and this is the capstone project, build your own ChatGPT style systems. The name which I mentioned here, character level tokenizer, for example, here, or word level tokenizer here, all of them are the programs that we will be writing here. Okay. So, for example, if I go to my code, Dream LLM code, so this is what I'm going to show you here. So, you will see this is the code that we'll be writing again from scratch. Okay, so this is what we will be writing. I already have written every single thing beforehand. All of the demos are also ready. So if I go back here, I can see these are the code, you know, something like character level tokenizer, how does it work, or what is a word level tokenizer, or subword tokenization, BP it is known as, you know, all of these codes are already ready. So we'll be kind of going through all of them. I mean, not only for that, under embeddings, you can see embedding visualization, similarity, contextual meaning, attention and transformer weight, all of these things which I'm mentioning here, all the demos are already ready and we'll be kind of going for every single one of them. Under RAG, we'll go for embedding. There are total 32 demos and 33rd is our final demo, the capstone project. This is what the Dream LLM here is, you know, this is what we are kind of building in this particular course. I mean, all of these things we'll be doing from scratch. This is more important, from scratch. Okay, fine. So if I want to do all of that stuff and if I want to do something like this course, what are the prerequisites? Couple of you are asking the question again and again. So let me answer this question. What are the prerequisites for this course? Again, please pay attention to them. This is again not for everyone. I mean, this is for those who are kind of fitting in this criteria. And believe me, you all can fit in this criteria. Number one, you need to know basic programming language, especially Python. And this is must have skill. Without that, you cannot write a single piece of code. As I showed you, all of these programs that we are going to write here, 33 programs, 33rd is the last one. It's like the final project. But 33, 32 small scale programs and 33rd is a build. It's a last exactly, you know, the capstone project that we are going to build. All of them are written by using Python. Don't worry about PyTorch. I'll tell you what PyTorch is and how do we work on that. Day after tomorrow, we'll start working on that. But what we need is Python. That's a prerequisite. Basic logical and problem solving skills. I mean, if you're a programmer, you might be knowing that. A basic math awareness, not expertise. A high school math is more than sufficient. High school math is what am I expecting? Not more than that. High school math, addition, subtraction, maybe division, multiplication, sometimes matrix, nothing more than that. You know, all the things that we are going to see or we are going to need, we'll see here in the class. Like, what do you mean by vectors? What do you mean by matrices? What do you mean by dot matrix? What do you mean by multiplication of matrices? All of that stuff we will be seeing here in the class, starting from day after tomorrow. No prior ML or AI knowledge is required. You don't have to know AI. You don't have to use ML. You just need only one thing, that you already have used a ChatGPT. Not like as a programmer, as an end user, you must have used a ChatGPT window, must have given some question, must have gotten some answer. If you know that, it's more than sufficient. Basic system setup, very important. No GPU required. Couple of you asked the question couple of times. I kept your question and answer right now. No GPU is required for this. All the demos that I've written here, all of them are running on CPU. We do not need GPU. If you are having it, well and good, but GPU is not the requirement of this course. Okay, One more time, GPU is not the requirement. Huh? Uh, in 1 or 2 demos, when I'm having a huge data, I may switch on my another machine, which I already have got a GPU there. I'll show you that how fast it is, but it is not the requirement of the course. We are going to run all our code, all our demos on CPU, not on GPU. What you do not need, you do not need a PhD in maths or in AI or in ML. You don't need that. You don't need advanced math degree, as I mentioned. You don't need prior transformer knowledge because we are going to start from scratch again, and no prior NLP language experience. You don't have to understand NLP. You don't have to understand transformer. Everything that we are going to need, I'll show you here in the class. Everything from scratch, and that's why I mentioned here. When we are talking about the course name, building your own LLM, this word is very important. From scratch, everything is from scratch, everything. Do not worry about that. We'll start with literally hello world program, and we'll build our own LLM and see how that LLM start generating the answers of the questions that we will like. This will be an awesome experience if you are kind of willing to join. Let me see a few questions, and then we can stop for today. Okay. Okay. So who's that? Shivam, in ChatGPT, there are no options like the deep thinking, fast answer, math, computation. How does a ChatGPT process differently? Hold on, we'll talk about that later. But what do you mean by thinking? So it does not think, as I mentioned last time. But still, what's the meaning of that? I'll explain that when we go for transformers. Ritesh, you took the name of Vaswani. Yes, attention is all you need. His information is came today in Lokmat newspaper. Oh, really? I don't read newspapers, so I'll have to check it. Vaswani is the person who is behind the entire Transformers, is the brainchild of it. Who's that? Lakraj. Do we need a high-spec laptop for that? I think you already got the answer now. No, you do not need high-spec laptop. You do not need GPU. Simple CPU would work. 8 GB RAM is what am I expecting today. I mean, of course, all of you must be having 8 GB RAM. At least I'm saying 16 GB is good enough. 8 GB is also okay. There is no problem. And GPU is not the requirement. Pranay, why do we not using TensorFlow? When you are going for TensorFlow, 70 code lines becomes one line code, and everything is done by TensorFlow behind the scene. You do not understand any damn thing. That's why I hate TensorFlow. Uh, PyTorch, on the other hand, you have to write lines of code, but this will give you a clear-cut understanding what exactly you are doing and what exactly is happening there. That's why PyTorch. And more or less, when you are going for research-oriented tasks, we generally prefer using PyTorch than using TensorFlow. TensorFlow is for production. PyTorch is for learning, and we are learning here. That's why PyTorch. Parameter as well. Yeah, of course. Without parameters, you can't do anything. Siddharth. Parameters, there are two types of parameters, weights and biases. More on that 2 days after tomorrow, I believe. Or maybe in the next week before we go for transformers. What's the use of epochs? Ashish, at the moment, epochs are nothing but repetition loops. More on that when we go for transformers or when we go for training the transformers. Right now, just understand, epoch is nothing but a loop. A number of times you want to run that loop. That's it. It's like a for loop, you can see. Indrajit, do we need to train it every time? No, of course not. I mean, I am not saving the model once it gets trained. That's the reason I need to. But otherwise, you don't have to. Once it is trained, you don't have to train it again. I mean, unless the data is changed. But you don't have to do it every single time for sure. Nitin, please suggest some nice books on to go. Yes, I will. In tomorrow's. Should I? Why not? Hold on. That reminds me. By the way, this course, the one that I'm using right now, the one that we are going through, this course is based on 3 major books. One of them, I mean, why I use this course, I mean, why I use that name is like build LLM from scratch. This is the book, and this is the very, very, very nice book. This is the book that I read, page to page multiple times. It's a very nice book, and this book I read in last February. This gave me an intuition behind this course. I mean, this is what I'm following right now. This is book number 1. This book name is its name is Sebastian Rashka. This is the person, very nice person, and this is the build your large language model from scratch. This is the book that I refer as a reference book. This is number 1. Second one is called as AI Engineering. This is the one, AI Engineering. Very nice book. Probably I can show you that here. If I can. This is the one. Chip you want. Very nice book. Very, very nice book. This shows you all the deployment and all the other stuff. Another one, math. What is the name of that? One second. I always forget the name of that book. I mean, I purchased that book. Here it is. Can we? Where the hell are you? Where are you here? Not this one. That's a machine learning. Where are you? Where are you? Where are you? Math book. Huh? Math. This is the one. I always forget the name of that book. So this is the one. Math and Architecture of a Deep Learning. This is another very nice book. I mean, this is the one that taught me all the maths behind it, like the vectors, matrices, tensors, and all of that stuff. I mean, this is a very nice book, and I think it's almost like around 600 pages of book. I mean, all of these three books combining together, I'm kind of going through it. Okay. So probably who asked that question? Nitin. This is the answer to your question. The other three books I'm referring to. This book, I purchased it. It's a very nice book. And this is the book which I mentioned right now. This is called as the Build Your LLM or Build Your Large Language Model from Scratch. This is the book, you can say. This is the book. This is the diagram which I mentioned earlier. It is derived from that book. I mean, everything which we are going through is kind of derived from this book. This is a kind of, you can say, the reference book for me, you can call it as. And the third book is the AI engineering. This is, I think I should be having this one also. Here it is. This one here. This is what the AI engineering book here is. Chip Yuan, the name of that person who has written this one. Very nice book, but very, you can say, very production oriented. It's like this is the book. So these three books I have referred. More than that, I have 6 more books in my bookshelf right now, but more on that somewhere later. But these are the 3 prominent books that I'm using for this entire course here. Nitin, answer your question. Girish, SLM run on the normal CPU with the good configuration. Can we say SLM is the app expert in the tailor? Yeah, of course. SLM and LLM, both of them are almost similar, as I mentioned. It's just like huge data, L, small data, S. That's the only difference. Will you please share some resources and well understood for the concept? Of course, Ashish, the books which I already mentioned, you can definitely go through it. Okay. Why GPT is decoder only? Hold on, we'll talk about that. We haven't talked about transformer yet. Unless we talk about the transformer, I can't talk about a decoder. So, Divakar, you will get the answer next week, I think on Wednesday or Thursday. Okay. We'll be deploying on Azure too. No, I'll be deploying on AWS. If you want Azure, you can do that on your own. Everything will remain same. It's just the cloud provider will change. Okay. Steps will remain same. Zahir, knowledge of Python, meaning the loops, list, tuples, classes, construction and destructors, NumPy. That's it. Nothing more than that. And pandas. That's it. Pandas is also not required. You can directly use the Python open function and get the job done. Pandas is also not required. NumPy is little bit required to a certain extent, but otherwise that is also not required because we are directly not going to use a NumPy anywhere. We are going to use TensorFlow a lot. Sorry, not TensorFlow, PyTorch a lot. So Tensor is something that I'll cover everything, whenever it is required. So don't worry about that. What kind of data are we planning to use for training? Textual data. Maybe you can call them as a free books. So we'll be using free books, not this one. These are the paid books, but the free books that we will be using, and then we'll be kind of learning from that, or maybe using that for training purpose. Who is handling your camera? Nothing, me, in fact. It's kind of shaking right now because I'm writing it down. That's the reason. It's macOS autofocus. Yes, Shubham, that's a macOS. New feature, autofocus. What is a LangChain? LangChain is a framework, Neeraj, which is used for communicating with all the API, all the LLM students. So if you want to use if you want to use GPT, Claude, or something, the LangChain is one of the frameworks which can connect to any of the LLMs out there. Okay. Can you share PDF? Of course. Which one? These PDFs I can't because I purchased them, and if I'm purchasing them, then it's like I'm bound to not to share it because that's how it goes, right? I don't want to, but there are different sites where you can download them free of cost. I mean, I hate that because I know these people have put very much efforts. This is like the bread and butter for them. So give them some respect. That's the reason I generally purchase the books. And when you purchase, when you purchase the book, you can definitely get the PDF file as well. Okay, but I can't share them. Sorry for that. And it's not like I don't want to share them, but it's like I'm bound to do that. I mean, when I purchase something or when you purchase something, you are not supposed to share that, because that's how the authors are getting their money, and all of us are looking for money, isn't it? So probably you can understand the seriousness of it, right? Aishwarya, I don't know the Python much, but I know the Java. No problem. We can, I mean, you can learn Python if you can on your own, and then you can continue further. No problem. Absolutely. What's the difference between NumPy array and tensor? NumPy array can work only on the CPU, and tensor can work on the GPU. That's a major difference. Otherwise, tensor is kind of using NumPy array behind the scene. That's a major difference, Pranay. Okay. Shubham, can we build LLM which we can run locally on a mobile device? Not mobile devices. Locally, yes. We'll be doing it on locally and we'll be deploying it on the AWS as well. Yes, we will be doing that. Okay. If we get any doubts in any steps, will there be separate sessions? Yes, Lakraj, let me mention that the course will go from Monday to Thursday, not on Friday. Monday to Thursday, same time 9 to 11, sometimes 11, sometimes 11:30, but 9 to 11 is most of the timing that will adhere to. Every alternate Fridays we'll be having a question answer sessions. So Lakrash, that's an answer to your question. If you are having doubts, if you see your question is not being answered because of the topic that we are looking at, you can put this aside and ask the question in the Friday's question answer session. Okay. So whatever the topics that we have covered in 2 weeks, we'll be discussing them in the next week. So it's like next week, Friday, we'll be having one extra session. We'll be talking about the question answers there. I'll answer all of the questions that you are having in your mind. So on the topics that we have covered. It's not like I don't want to answer the other questions. I can, but the point here is whatever that we have covered, whatever the question that you are having, write them down and answer them in the question answer session. Okay. Nikhil will also learn the vectors in this course. No doubt, without vector, you can't do anything. So yes, day after tomorrow, I'll start talking about the math behind it, like the matrices, the vectors, the vectors operations, matrices operations, and all of that stuff. So math will start day after tomorrow, Wednesday. Yep, Nitin, thank you very much. Yes, someone is raising hand. Yashad, you're raising your hand. Please go ahead. Yashad, you are raising your hand.
Sir, am I audible?
Not able to hear you. Is that me or is that you?
Am I audible?
1 second. Let me see if that is connected to my. No, it is not. I'm not able to hear you. 1 sec. No, not able to hear you.
Hello? Am I audible,
For
sir?
some reason, you are audible, but for some reason I am not. 1 second. Let me see if my audio is switched to something. External microphone. An external. That's the reason. Can you say something again, Yashar, please?
Sir, am I audible now?
Yes, you are. No problem. Please.
Thanks, sir. After a
Yep.
long time.
Yep.
So, sir, recently I have been through one of the interviews. So the
Mhm.
interviewer asked me why we can't use the traditional databases like SQL and NoSQL databases in storing the data for in the form of vector while working with LLMs. So I
Right.
tried to convince him, but somehow I can't.
Uh,
Can
ca- can I put your question on hold right now because we haven't talked about the vectors yet? I can answer that on day after tomorrow when we talk about vectors. So you
sure,
can
sure.
understand why not the traditional databases and what special thing that vector database can give you. I'll answer the question right now, but more the explanation will come on Wednesday. Because traditional databases cannot give you cosine similarity, which is what the vectors can give you. What do you mean by that? Wednesday, you will understand.
Okay, and
Okay.
that's what makes LLMs much faster.
Yeah, not faster, more accurate. It's not for being the faster, it's because of the limitation on the context length. Again, more on that next week. But right now, because every LLM has got a fixed context length and you can't pass more than that context length. So be reasonable in that particular range. We go for only the context that you need to answer your question, and that similarity can be found easily by using vector databases, which is not possible in your regular databases. That's the reason. Okay. But more on mathematical side of it on Wednesday. Okay.
Thanks a lot, sir.
No problem. Fine. Okay. Fine. No worries. Chalo. So if there is no question left, I think you got your answers, I believe. So better we can stop here for today and we'll continue tomorrow. Okay. Okay. Again, thank you very much, guys, for attending today's session. I hope you must have found it bit kind of revealing some of your answers, hopefully. And hopefully I see you tomorrow also. So tomorrow we'll be talking more about tokenizer. So we'll see like what's the tokenizer, how the tokenizers work, and what are the different types of tokenizers that we can code. Okay. So tomorrow we'll talk about character tokenizer, word tokenizer, and byte pair encoding. It's called the BP. Okay, so tomorrow will be a little bit, we are starting with our first part of it. Sure. Good night, guys, and thank you very much. See you tomorrow. Bye bye. No problem, okay? No problem.